Thanks everyone for joining. Thank you for waiting for 5 minutes for this quote to finally be completed. So let me just start with that. The future of computing is heterogeneous because we see more and more that compute-heavy applications are moving from general purpose processors or CPUs to domain-specific accelerators, which are hardware accelerators that are optimized very specifically for certain tasks. And in this context, FPGAs are interesting because they are reconfigurable and they do not have the same upfront costs that ASICs do, but also not the same lead times. They're more flexible. And so there's demand for FPGAs, and where there's demand, there's supply. And so we see that in the cloud, different CSPs like AWS, Alibaba, and Azure are providing means for FPGA acceleration in the cloud. Now, of course, the economic model is still the same, being push as many tenants as possible on the same shared resources, so on the same physical device. And over the years, we've also come to learn that shared resources means side channel attacks, like cache attacks, for instance, where an attacker on the same physical device spies on other processes by means of their interaction with the cache hierarchy. And so during the years, we've seen cache attacks being mounted from the CPU. Very recently, we've also seen some being mounted from accelerators like FPGAs or network interface cards. But what this work wants to do is put forward a new kind of attacker model, being that of a combined attacker who controls at least one CPU core and one what we call secondary device. So this can be an FPGA or a network interface card. And this is the topic of our paper, Double Trouble. So this is joint work with Antoon Purnal and Ingrid Verbouwede from IMEC COSIC at KU Leuven. And my name is Antoon Purnal, and I'll be presenting this work. So how do secondary devices like FPGAs interact with the memory subsystem? Well, let's look at some preliminaries first. So we're going to focus on the Intel server segment, because that's often what's used in the cloud. So those are Intel Xeons. And like many other processors, they have a memory hierarchy consisting of multiple levels of caches. And caches are hardware buffers that store data that is going to be that the CPU thinks is going to be reused. The memory hierarchy typically has, in Intel processors, at least 3 levels. So there's the L1 and L2 that are close to the core and that are private to the core. And then we also have the shared last level cache, which is, as mentioned, shared among all the cores. Now, of course, as we move from closer to the CPU to RAM or memory, these caches get larger, but also the access times also get larger, which means that there's an inherent timing side channel here that an attacker can exploit to infer activity, basically, in each of those cache levels. And the literature has heavily focused on the shared last level cache because it's shared, and so one core can attack another core. But recently, these last level caches have kind of changed topology in Intel servers. So they've moved from inclusive to non-inclusive designs, which has some challenges that will, among other things, try to solve in this work. But then how do the secondary devices come in, right? So we have an FPGA or network interface card here. And to maintain performance, this is as tightly integrated with the CPU as possible. And on Intel CPUs, this happens with a technology called Intel DDIO that basically pushes all the memory traffic of the FPGA through this shared last level cache. So this speeds up performance because the FPGA now interacts with a fast cache instead of a slow memory. But as we will see, this provides an attacker with another interesting anchor point into this last level cache. So then, what's an FPGA? So FPGAs implement reconfigurable hardware, and they do so with a huge array of lookup tables and flip-flops. which implement logic, any kind of circuit you want, and then flexibly interconnect those at synthesis time. And we see FPGAs being emerging in the cloud as PCIe acceleration cards. And in this context, some recent acquisitions are noteworthy, being like the big CPU manufacturers purchasing or acquiring the big FPGA vendors. So this is a trend we're clearly seeing. Now, from our attack point of view, the only thing we need on this FPGA are two things. Basically, a way to interact with memory, and that's going to be DMA, or direct memory access. And we're going to do a timing side channel attack, so we need a way to measure time. And this is trivial on an FPGA. You can just implement a counter, and this will serve as a perfect timing source. Okay. So we know now that these secondary devices interact through the last level cache, but in terms of what they can do, they're really second-class citizens compared to the CPU. So if we have our memory here and our last level cache here, if our secondary device performs a read of a certain cache line, right, this will serve the cache line to the secondary device, but it will not allocate it in the LLC. If, on the other hand, the secondary device performs a write, then, of course, the write gets through to memory, but then we do see that the line gets cached in the LLC, but only in a certain small sub-region of it. And this is also being a second-class citizen. All the DDIO traffic is limited to, by default, two ways, which we call the DDIO ways. And this is to ensure that the performance of the CPU the performance of the CPU is preserved if you have a secondary device that's generating a lot of traffic there. So, but is this always two ways? So no. So someone with privileges can change the configuration and increase the number of ways used for DDIO, even up to the full LLC if they want. But the default case is two, and that's also what we're going to focus on. Okay, so reads don't allocate in the LLC. So that's lines that are not already there. How about lines that are already in the LLC? Well, there also we note something peculiar, and that's that these reads are ignored in all the kind of metadata bookkeeping in the cache. So normally, if we have a cache set with two lines and x0 is about to be evicted, like if we perform writes with the secondary device, we see that now the cache will favor to replace x1, which makes sense. But for reads, we don't see this happening at all. So for reads, it's as if they don't happen. They're invisible. And then as a final deep dive part into the interaction between secondary devices and memory, let's look at cache transactions. So that's basically, we're studying the LLC, okay? So we want to know how lines can be moved in and out of it. And because we consider ourselves to be this double combined attacker, we can do some FPGA-assisted reverse engineering because we look at this hierarchy from two sides. And there we discover, so this is known, that you can move lines from the core to the last level cache through L2 evictions, but also by accessing a line from two different cores. This is new. And also, of course, by writing to the line from the secondary device. You can also do the inverse thing, so you can write or read with the CPU, and that will move the line back to the core. Now, some of our findings here contradict those in prior work, so we provide supporting experiments with hardware and software as part of our GitHub repo or open source repo for future research. But so all in all, summing all of this together, an attacker has very fine-grained control over where lines end up in the cache hierarchy. But on the other hand, the attacker is also very limited in some of those interactions. And we're going to use the fine-grained control as an advantage, but we're actually also going to turn these restrictions around into advantages. And we'll see how to do that. So we have a few implications in the paper of this fine-grained control. in this talk, I'll probably only have time to go over 2 in detail. So let's look at the eviction set problem first. So the eviction set problem basically amounts to finding at runtime addresses that map to the same last level cache set. And so our hardware accelerator on the FPGA achieves in doing this in under 200 microseconds, which is between 1 and 3 orders of magnitude faster than prior work. So how does it do this? I'll walk through the algorithm in detail here. So we're assuming we want to construct an eviction set. So we want to find lines that map to the same set as a target T. So we start from a big pool, of which some lines will be congruent, so they will map to the same set, and those are green here. So what we do is we write with the accelerator to this target T, and then we just write guesses. And so this one, G0, is congruent to T, but it still doesn't evict it, like there's still room in this cache here, in this set. So we don't observe this, and our target read is still fast. It's not evicted yet. And then we try more and more guesses, so we go through the pool until at some point we get another address that is congruent to the target. Now it evicts it, we see it as a slow read, and that means that G5 must be congruent with the target, easy peasy, and we have a first element of the eviction set, and we can basically then repeat this, but as we get more lines, this gets faster, because the first one will not be invisible anymore if we fill it with G5 and target. So that's what we do in the next search, and then we basically do this until we have enough lines, and then we have our eviction set. And the reason why this works at all is because of these invisible reads, which were thought to be a restriction of these secondary devices. So that's why it works at all, and the reason why it works even faster is because this DDIO region is so small, so it's easy to evict other lines. All right, we also have another finding of an undocumented structure within Intel processors, and that's, for that, let's consider the following case. So assume this secondary device performs a write, but only after one of the CPU cores has already written to it. Then what happens? So we see that it still goes to the LLC, but outside of this publicly known region. That's interesting. So what we then did is, again, FPGA-assisted reverse engineering, and then we found out that there's actually 2 more ways that are used for special purposes. And we call these, well, we were the first to find them, so we could name them. We did stick with the boring name, so we called it the DDIO plus region. And basically, lines that are in this state will get pushed to these ways instead of those. And then you might wonder, well, does this hold for all DDIO configurations? What happens if we make that bigger? And we did the reverse engineering for that too, and then we find that this DDIO plus region persists all the time. It's always 2 ways large, it's always in the same location. And if your DDIO configuration is high, then there's even some overlap between the regions. So our attacker control was already precise because we could enforce to which level in the hierarchy a line would be mapped. But now we can also fix the line within the set, which to our knowledge is kind of unprecedented. So in the interest of time, I'm going to speed run through all the other contributions in the paper that are enabled by this fine-grained control. So one of them is that we show how to evict shared lines with tiny eviction sets, so with many fewer lines than you would think you'd normally need. And the key to do that is to invalidate specific ways in the last level cache, which we now know how to do, right? We also use the knowledge we found to evict shared lines from other cores and even other CPU sockets without generating contention on the directory or without flushing. This is also new. And this revealed some interesting cache transactions that we exploited in an end-to-end attack on AES. And finally, we also implemented a fine-grained covert channel that encodes information in how many lines that are being evicted, which is also something that hasn't been shown before. And we also encode this in the DDIO. This is again this fine-grained control over the set that we use there. So in conclusion, we built a FPGA-based hardware combined cache attack as a service accelerator, which, by the way, you can sell these accelerators on the marketplaces of these cloud vendors, which we obviously didn't. But what we did do is open source both our hardware and software for reproducibility and future research. We also conclude that FPGAs are interesting in this regard because they trivially provide their own timer, which is noise-free, it's unrestrictable. FPGAs also run all the time, so they're not interruptible by the CPU. And the components we need to mount our cache attacks are so small that they're almost imperceptible when looking at the whole FPGA fabric. So they're very hard to detect. We also conclude that countermeasures for combined attackers are quite tricky in the sense that some of the advantages that a combined attacker has are exactly because it's being restricted. Because it's restricted to these ways and because reads are not allocating, that's actually what enables us to do more advanced attacks than people could have done before. So restricting it more might have adverse effects. So yes, the future of computing is heterogeneous, but let's not underestimate the complexity that this brings and the new attack surface it opens. And let's revisit common assumptions we have on microarchitectural attacks and defenses. That's it for the talk, and I'd like to take questions now, if there are any.